So I'm Carlee, and I will be presenting, as Mung said, on multi-resource allocation and focusing especially on fairness considerations in doing these resource allocations. So this is joint work with Soumya Sen, who is a postdoc in the lab, and Tian Lan and Mung. So the main question that I'll be considering in the talk kind of goes like this. So suppose you have multiple non-substitutable resources. Like here, we just have apples and oranges. And these combine in some sort of ratio to make something that people want. So in this case, maybe fruit salad, or you could consider a more general case. But you only have finite amounts of resources. So the question you want to answer is, how do you simultaneously allocate these multiple different resources to different people? So to help you kind of see where the challenge in this lies, I've put up here just a two-resource example. So here you have 6 apples, 4 oranges. So we can say we have like one user who maybe needs like 2 apples and 3 oranges per job, and another user might need 2 apples and 1 orange per job. So you can see that different users need different mixes of the resources, and it's kind of not an easy question to answer as to how you can simultaneously allocate the different resources given these different resource requirements. So I've been using apples and oranges just to illustrate that this work is kind of very generic and can apply to any multi-resource scenario. But the main motivation behind the work is basically cloud data centers. So here we can envision kind of a data center in the cloud, and it has jobs coming from multiple different users. And these jobs have different resource requirements, and their resources might be something like CPU processing, RAM, or link bandwidth. So in this case, you have to try to allocate these different resources to all of these different users and different jobs. So first, just a little bit of background on single resource fairness. So of course, fairness is, as Mung said, a widely debated topic, and it goes back probably thousands of years. And it's been debated in many different fields of academia. So I won't really go over all of the different single resource fairness theories. So most of these theories do focus on a single resource. But I will highlight one approach, which is the one I'll kind of be adapting to the multi-resource scenario, and that is that of fairness functions. So the idea here is that if you have many different users and you just have one resource, then you can form a vector which represents your resource allocation. And each entry of the vector is just the amount of resource allocated to each user. So then you can plug this vector into a fairness function, and that spits out a scalar, or just a number. That quantifies the fairness of this resource allocation. So here you can see what we call alpha fairness functions, or isoelastic functions. And these are often used in engineering and economics when you're dealing with the fairness of a single resource allocation. However, in 2010, Tian and Mung showed that these are really just a subset of a much larger family of fairness functions, which satisfy 4 or 5 different axioms. So I won't present the axioms here, but this is kind of what the function looks like. So this is the type of fairness function that I'll be kind of adapting later to the multi-resource case. So again, if we go back to our 2-resource example, we can see that it's not entirely clear how you might map the single resource function, where you have this one vector of the amount of resources allocated to each user, into a multi-resource context. So maybe one sort of intuitive way to do this is to say, okay, I've assumed that these multiple resources combine to make some jobs. So this one thing that the different users want. So maybe what I should do is I should just take the number of jobs and stick that into the fairness function. So this is a framework that I'll call generalized fairness on jobs. And the justification here is that if I'm a user, my utility isn't really affected by the amount of resources I receive. It's more affected by the number of jobs I can process. So in that sense, it makes sense to just look at the fairness of the number of jobs allocated to each user. So this vector x here just stands for the number of jobs. But that might not be the best way to go about this. And let me explain why using this example again from the beginning of the talk. So if you asked me what is the most fair thing to do in this scenario, I might tell you to just allocate one job to each user, because then you have a very equitable allocation. But it's not very efficient because you only get sort of 2 jobs done in total. So this is kind of what I'll call the fairness component of the fairness function. So I'm sorry for the kind of confusion in terminology. But this is sort of looking at the equitability of a resource allocation. And this expression here is how we evaluate that equitability. So you notice here that we have this parameter beta, which kind of lets us suggest how we evaluate this part of fairness. But there's another part of fairness, and that's kind of efficiency. So the idea here is that the more jobs you can give to all the users, the better off all the users will be. So in that sense, this allocation might be more fair. So if you ask me to look at this example again and say, what is the most efficient thing to do, I might tell you to just give 3 jobs to user 2 and 0 jobs to user 1. Because then you can actually get 3 jobs done instead of 2 jobs on the previous slide. So that seems a lot more efficient. But obviously it's not as fair because user 1 doesn't get any jobs done at all. So that's why we have this other term in the fairness function, which I'll call the efficiency term. And this basically takes the total amount of resources, the total number of jobs allocated to all users, and raises it to a parameter lambda. So lambda here weights the importance of efficiency relative to this equitability term that I discussed on the previous slide. So you can see here that there's kind of a trade-off between this equitability or fairness and efficiency. And that comes from the fact that users are heterogeneous. They don't have the same resource requirements. So you might say then that it would make sense to incorporate these resource requirements into the fairness functions. And one way to do this is through what we call dominant shares. So these are first introduced by Ali and co-authors in 2011. And let me just explain what they are. So the scalar mu that I've defined here is defined for each user. So j here indexes a different user. What I've done here is I've taken Rij, which is user j's per job requirement for resource I, and I just divided it by the capacity of resource I. So it's the fraction of the resource that this particular user needs. And then I just took the maximum over all the different resources. So, for instance, in this example, if we just look at user 1, we can see that user 1 needs 1/3 of all the apples and 3/4 of all the oranges to complete one job. So this mu1 would be 3/4. And you can do similar calculations for user 2. So now Goetze's idea was to take these dominant shares and just to do max-min fairness on them. So max-min fairness is one popular notion of fairness. And what you end up doing here is you just end up equalizing the dominant shares, which are mu, this scalar that I defined on the previous slide, times the number of jobs that the user receives. So if you try to equalize this, it's easy to see that the larger your mu, the smaller your x will end up being. And that kind of intuitively makes sense. The larger the share of resources you're taking up, the fewer jobs you should get in the end. So in this work, we kind of generalized this max-min fairness on dominant shares, what's Goetze called dominant resource fairness, to what I call fairness on dominant shares. So the idea behind this is that max-min fairness is kind of an extreme view of fairness. It only looks at the worse-off user. So you can generalize this by just taking the dominant shares and plugging them into these single resource fairness functions that Tian had derived in his thesis. So here we get a different family of multi-resource fairness functions. So now if you take a step back and look at this generalized fairness on jobs and fairness on dominant shares, you can kind of see what they're doing. So we can start out with this matrix of resource requirements for each user. And then we scalarize those resource requirements. So if you use generalized fairness on jobs, you can scalarize this just by taking the number of jobs. If you use fairness on dominant shares, you scalarize it by taking the dominant share. So then you end up with a vector where you have one scalar representing each user. Now you can plug that into your single resource fairness function, and in the end you get a multi-resource fairness measure. So given these multi-resource fairness measures, we can look at the properties they satisfy. So I'll be talking about 3 properties: Pareto efficiency, sharing incentive, and envy freeness. So the first property, called Pareto efficiency, basically says that if you have 2 allocations, x and y, and x Pareto dominates y, then x should be more fair than y. And by Pareto dominate, I mean that each user is at least as well off under allocation x as under allocation y. So you can derive conditions on these beta and lambda parameters. So beta, again, parameterizes fairness. Lambda parameterizes the importance of efficiency. And if lambda is sort of large enough relative to beta, then Pareto efficiency holds. And I'll just note here that at the threshold, when lambda equals 1 minus beta over beta, you recover these familiar alpha fairness functions with alpha equal to beta. So I'll be using that when I talk about the next two properties. So sharing incentive and MJ freeness both deal with the sort of optimal or most fair allocation. So let me just pause here to look at what the optimization problem actually is. So here our objective is to maximize fairness, but we have some constraints, which have to do with the resource constraints. Basically what it says here is that if I assign a certain number of jobs to each user, I'd better have enough resources to actually execute those jobs. So the sharing incentive property says that if you look at this optimal or most fair allocation, then each user has to be at least as well off as if you had just taken each resource, chopped it into equal chunks, and given an equal chunk to each user. So again, we can derive parameter conditions under which this does and does not hold. If you look at fairness on dominant shares, then taking alpha equal beta fairness for beta greater than 1, the sharing incentive property holds. On the other hand, if beta is less than 1, then you can derive counterexamples. And if you look at generalized fairness on jobs, you can actually derive counterexamples for any value of beta. Now for MV freeness, you can actually derive the same parameter conditions. And the definition of MV freeness is that no user envies another user's allocation. So users don't want to switch allocations. So again, yeah, the same parameter conditions. And this kind of visualizes sort of when sharing incentive and MV freeness do and do not hold. So in the top graph here, I've looked at parameters for fairness on dominant shares. At the bottom, it's for generalized fairness on jobs. So you can see that in the generalized fairness on jobs graph, you have these huge regions of the parameter space, so different lambda and beta values, where you can find counterexamples. So that kind of indicates that, in general, neither of these properties seem to hold for these GFJ fairness functions. On the other hand, if you look at fairness of dominant shares, you do find parameter values where you can prove that sharing incentive and MV freeness do hold whenever you do this sort of multi-resource allocation. So in that sense, if you want these properties to hold, maybe it's better to look at these fairness on dominant shares instead of generalized fairness on jobs. So now let me go back to something I mentioned when I was just sort of formulating these two different fairness functions, families of fairness functions, and that's to fairness efficiency trade-offs. Now one way to look at the fairness efficiency trade-offs that are possible is to see when the trade-off doesn't exist. So when can you maximize efficiency and maximize fairness at the same time? And we can derive conditions under which this holds. I won't really go into what these mean or how they're derived. But what I will note is that these gamma ij scalars here are just functions of the resource requirements and the capacity of each resource. So what these conditions basically say is that if your resource requirements line up exactly right, then you can maximize fairness, then you can maximize efficiency. Otherwise, you will have some sort of trade-off. So now we can numerically look at what sort of trade-offs you can observe. Now this doesn't show much about fairness, but it does show the range of different efficiencies that you might come up with for a range of fairness functions. So here, these are the resource constraints that I've been looking at, and what I did is I just varied this number 18, which is the capacity of the second resource. So here you can suppose it's memory. And I varied that between 4 and 26, and then I plotted the efficiency achieved for different fairness functions. So you can see that this dark gray region below represents sort of efficiencies that were only achieved by generalized fairness on jobs. But on the other hand, the light gray region could be achieved by either type of fairness functions. So GFJ kind of seems to have a wider range of possible achievable efficiencies. So now if we look at the trade-off between fairness and efficiency, we can get graphs like this. So this is for the same example. And on the x-axis, I've plotted the sort of percent fairness, which is the fairness as measured by dominant resource fairness divided by the maximum DRF value. Same for efficiency on the y-axis. So again, I just vary the capacity of the second resource. And you can see that as you sort of increase this from 4 gigabytes, the trade-off curve moves towards this upper right corner. And if the capacity is exactly 6 root 3 gigabytes, then the resource requirements line up exactly right, and you get 100% efficiency and 100% fairness at the same time. So there's no fairness efficiency trade-off. Now, as you keep increasing the capacity, the trade-off curve kind of goes back down, and you have a greater range depending on the parameters of your fairness function. So that's kind of all I have to say about the theory behind the fairness functions. But in the last part of the talk, I'll present some research we've done on how this kind of maps into users' actual perceptions of fairness. So there were two questions that we wanted to address here. One is, do users agree with each other? Do they hold similar views on fairness? And the other is, can we find parameters in our theory that correspond to users' views of fairness? So the way we went about addressing these questions is by conducting an online survey. So we asked people to pretend that they're a data center operator, and then that they have these two different clients, and each client has requirements for memory and for CPU. And then we gave them a bunch of different possible resource allocations, and we just asked them to rank the allocations in order of preference. So here I've kind of given one sample question. So note that we computed for people the total number of jobs completed for different possible resource allocations. In other questions in our survey, we instead looked at the leftover capacity, which is another efficiency metric that you could measure. So our first question was, are people's views of fairness sort of compatible? Are they similar? So on the x-axis here, I've shown the average perceived fairness value, which is basically just the fairness of all the different allocations, and then I took a weighted sum with weights based on people's rankings. And the same for the y-axis for efficiency. So on this graph, this is a graph that we could have gotten in which people are sort of very different, and each point here would represent one user, and the larger the circle, the more users there. So this is what we might have seen if people were very different. But what we actually saw is that people are very similar. So this is the graph that we actually derived for one of the questions in our survey. And you can see that users very nicely divide themselves into two different clusters. So cluster 1 kind of prefers efficiency to fairness. Cluster 2 kind of prefers fairness to efficiency. And now if we look at responses for all of our survey questions, you can see that in each of them people cluster together. And that's kind of interesting because we were varying things like resource requirements, like whether you use leftover capacity or the total number of jobs to measure efficiency, but we still got this very consistent agreement between users. So that kind of gives you hope that maybe we could map our theory into this sort of consensus view of fairness. So what I did here is I just looked at different fairness functions, so I took different parameter combinations, and the darker the square at this particular parameter combination, the more users' responses were compatible with that fairness function. So here I'm assuming users are using generalized fairness on jobs to evaluate fairness. So you can see that there's a fair number of parameters that are compatible. And you can do the same for this cluster too. And it's kind of hard to see here, but there are parameter values that are consistent with both clusters. So that sounds great. Now, if we assume that users are using fairness on dominant shares, you get a very different result, and that's this result here. So you can see that no parameters combinations were actually consistent with users' ranking of different allocations, assuming fairness on dominant shares. So that kind of ties back to these properties I was discussing with the different functions. So if you recall, I said that sharing incentive and memory freeness are more likely to hold with fairness on dominant shares. And these are often taken to be, pretty desirable properties for a fairness function. On the other hand, these results seem to indicate that if you go to real users, their answers are not compatible with these sharing incentive or envy freeness properties. Now maybe that's just because it's cognitively easier to look at just the number of jobs in fairness and not to look at the resource requirements, but I think it's an interesting result and it might deserve further consideration. So that's all I have today, and I'm glad to take any questions.